Okay, let's start today's notes. We are on notes number 9, and the title is Solving Systems of Equations, and today we are starting Chapter 3. I'm excited too. Okay, so here's the big idea of Chapter 3, talking about systems of equations. So in Chapter 2, we looked at equations of lines, and we know that if we have an equation like this, y equals 2x plus 1, that we have a line. If we graph the equation, we have a line. And we know that if we have the equation, let's say y equals the opposite of x plus 3, that we have another line, and let's say that it does something like this. So if we have both of them together on the same graph, then the lines might intersect depending on the lines. And so the intersection point is known as the solution to this system. So a system is having two or more equations, and the solution is the point or points that they have in common. So that's the idea. We're going to be solving linear systems of equations, but you could eventually solve a system of equations where one of your equations was, let's say, a parabola, and maybe the other one was, let's say, an absolute value, and you're finding all the points of intersection of the two. Okay, so for now we're focusing on lines, and there's some vocabulary that we're going to use as we talk about systems of equations. So first of all, we have the term consistent. A consistent system has one or more solutions. So I do want you to know this vocabulary. Okay, therefore, an inconsistent system has no solutions. A dependent system has infinitely many solutions. So think about what that would look like with two lines. How could you have infinitely many solutions? And then an independent solution has one solution. Or an independent system, I should say, has one solution. Okay, so let's imagine some different scenarios. Suppose we had a line like this and a line like this intersecting at one point. So this system is consistent and independent. It has one solution. Suppose we have two lines like this that are parallel. There's no solution because there's no point of intersection. So this is an inconsistent system. Suppose we have one line like this, and we have another equation which happens to graph to the exact same thing. So even though maybe the equations looked different, they're actually the same line. That would be a dependent system, and it would be consistent because it does have one or more solutions, but it would be dependent since it has infinitely many solutions. Okay, I think that takes care of our cases, so we don't really need 4. Let's go ahead and practice the different methods of solving a system that you've seen in the past. We're going to practice 3 methods: graphing, elimination, and substitution. And there will be times when you prefer to use one method over another. There will be times when you're told to use a particular method and times when you get to choose your method. So here we're told to use graphing. And so we have a choice. We can either change the equations into slope-intercept form, or we can keep the equations in standard form and find intercepts. So I'm going to go ahead and call the first equation A and use blue, and I'm going to call the second equation B and use red. And for A, I'm going to find the intercepts because that's my preferred method for standard form equations. If x is 0, then y has to be -8, and if y is 0, x has to be 16. Finding intercepts also helps you know what kind of scale to use when you draw your graph. And then for b, if x is 0, then y is 12, and if y is 0, x is 6. Okay, so it looks like I should go out to 16 at least on my x-axis and up to 12 at least on my y-axis. So I think I'll go by 2's. Okay, so I'm going to graph the first line, line A, and I'm going to plot the point 0, negative 8, and the point 16, 0. And it would be best to use a ruler. Okay, and now I'm going to graph line B, so I'm going to plot the point 0, 12, and the point 6, 0. And again, if you could, use a ruler. By me not using a ruler, I'm not having a whole lot of confidence in my point of intersection. So now I'm going to approximate this point of intersection. So I'm going to say it's about, what would that be? About 8, negative 4. Now what you could do is substitute those numbers into the equations and see if those numbers make both equations true, if you wanted to check. But when you're solving with graphing, oftentimes you're just approximating. 8 minus 2 times negative 4 is 16, and 2 times 8 plus negative 4 is 12. Okay, so it is 8, negative 4. All right. For number 2, we're solving the system by graphing, same system, but we're going to use a graphing calculator. So we may have done this in our class time together, but if you missed that, here's what we want to do. So I'm going to take equation A, and I'm going to isolate y. So we have x minus 2y equals 16, subtract x from both sides, divide both sides by negative 2, and that's the equation we'll type in the calculator. And then for the second equation, same idea, we're going to isolate y, so we'll subtract 2x, and that's the equation we're going to type into the calculator. Okay, so here's my graphing calculator, and we go into y equals, and if there's anything already there, then you can clear it, and if you want to, you can clear your memory. Remember, second plus, number 7 is reset, and then all RAM reset if you feel like you need to clear out whatever things were in there from before. Sometimes, especially if you have any scatter plots turned on from what you did before with your calculator, it can interfere with your ability to graph something new. Okay, so we go to y equals, and we're going to type in 1/2 x minus 8, and then for the second equation we have y equals negative 2x plus 12. Be sure to use the negative button next to enter and don't use the minus button because your calculator won't understand. Now we need to set good window dimensions, and you might try one of your preset window dimensions. If you go to zoom, you can try number 6, zoom standard, which shows you from negative 10 to 10 on both axes. That's a nice place to start, but if it's not sufficient, then you can change your window dimensions yourself. So negative 10 to 10 does show us enough to see the point of intersection of the lines. And then what we can do is go into the calculate menu, which is second trace, choose number 5, intersect, put the cursor on the first curve, press enter, put the cursor on the second curve, press enter, and then move the cursor closer to the point of intersection and press enter. And there you see at the bottom of the screen 8, negative 4. Okay. Now we're taking the same system and we're solving it by substitution. So if you recall, to solve by substitution, you need to isolate a variable in one equation. And it's really up to you which variable you isolate. You have a lot of choices. You're probably going to choose the easiest way, and then substitute into the other equation. So I'm going to call these equations 1 and 2. So I'm going to choose to isolate x in equation 1. So I'm going to add 2y to both sides. X equals 2y plus 16. That means I need to substitute into equation 2. So where I see the x, I'm going to replace it with 2y plus 16. So we have 2 times 2y plus 16 plus y equals 12. So because this system, or because this equation just has y in it, we can go ahead and solve for y. So let's distribute the 2, 4y plus 32 plus y equals 12. Add the like terms, 5y plus 32 equals 12. Subtract 32 from both sides, 5y equals negative 20, and then divide by 5, y is negative 4. Once you have that, you can go back to one of your previous equations and find the value of x. So we have x equals 2 times y plus 16. So that means x is 2 times negative 4 plus 16. And that gives us x equals 8. So then we can write our solution as an ordered pair, 8 comma negative 4. Okay, you always write your solution as an ordered pair, x comma y. So obviously that's the same answer that we got, doing it both of the ways we have previously done the problem. Now let's take a look at solving by elimination. And elimination is also known as the addition method or the addition-subtraction method. It has a lot of names. Here's the concept behind this method. If you had an equation like k minus j equals m, you could add 3 to both sides, right? And it's still a balanced equation. That's just a very elementary equation solving concept. Well, what if you knew that 3 was equal to triangle? Could you add 3 to one side of the equation and add triangle to the other side of the equation and have it still be balanced? Yes, you could. So, if I look at my system here, I have an equation and I have two things that are equal. This is 3, well, just pretend it's 3, and this is triangle. So I'm going to add 3 to one side of my first equation and add triangle to the other side of my first equation. So what I mean is I'm going to add 2x plus y to one side of my first equation, and I'm going to add 12 to the other side of my first equation. Or I could. I'm actually not going to do that, but I could, because it would still be balanced. But what do I really want to do? I don't really want to add those things. I want to add something to both sides of the first equation so that I eliminate a variable. So how about if we modify the second equation? What if we multiply it by 2? Then the second equation is 4x plus 2y equals 24. And suppose we keep the first equation as it is. Now, if I add this quantity to the left side of my equation and this quantity to the right side of my equation, my y terms will add to 0 and I will eliminate y. So that's the goal of elimination. So let's do that. We're going to add these equations together, and we have 5x plus 0y equals 40. Divide both sides by 5 and we have x equals 8. Now we go back in and we substitute to find the value of y. So if I go back into the first equation, x minus 2y equals 16. 8 minus 2y equals 16. So negative 2y equals 8. So y equals negative 4. You don't have to do elimination to find the values of both variables. Just use it on one and then substitute to get the other. Okay, so we have 3 more examples to do. What I think I'll do is just make those part 2, and we'll have 2 videos for today.